Let us now understand the concept of escaping light from a medium interface by a point source. To understand this, let's consider an interface between air and water. This is the boundary. Here in water at a depth h below the boundary, a point source is placed, and this point source originates light in all directions. And here we know that the light rays which are incident on the boundary after refraction, these will emerge out at an angle more than the incidence angle, because air is a rarer medium. The light which will incident normally will pass as it is, because the direction of light ray which incident normally on a medium boundary will never get deviated. And here we can see the light which is coming out must have the angle of incidence less than critical angle. So if we consider a light ray which is incident on the boundary from the source at an angle critical angle, this light after refraction will be passing along the surface, or this will have a grazing refraction. And in this situation we can consider all light rays from the source which are incident on the boundary at an angle theta c, and these all light rays will form a conical region in which all light rays which are incident on the boundary will be coming out of the medium, and those which are incident at an angle theta c, that means all those light rays which are on the lateral surface of cone, will have grazing refraction after the refraction from the boundary. Now in this situation, all those light rays which are from the source incident onto the boundary, which are beyond this cone, then these will be having an angle of incidence more than theta c. So these light rays will be reflected back into the same medium, that is water. So all the light rays which are going beyond this conical region, all those light rays will be having I more than theta c, and these light rays will not be able to escape from the water to air medium. So here we can say all those light rays which are within this conical region, which are forming a cone with a base radius r, where we can write if this angle is theta c, the base radius r can be related as tan theta c is r by h. So the value of r will be h tan theta c. This is a circle on the surface of boundary which can be regarded as the base of same cone, from which all the light rays are coming out, and any light ray which is falling on the boundary beyond this circular zone will not be escaping from the medium to air. So in this situation here, we can easily calculate the amount of light energy which is escaping to air from water by using the concept of solid angle, as here if we calculate solid angle of cone with the half angle theta c is, the solid angle we can write 2 pi 1 minus cos theta c. The relation in half angle of a cone and solid angle you can analyze from fundamentals of mathematics or basic mathematics section in the beginning of these lectures. And here we are calculating the value of solid angle, and using the solid angle we can find out the total light energy which is escaping from the water to air. Now if the source power is considered as P watt, we can directly write the power which is escaping from water to air is, this escaping power we can write as this total power was P, which is distributed in the complete three-dimensional region in a solid angle of 4 pi. We multiply it with the solid angle of this cone from which the power is escaping out. So this will be 2 pi 1 minus cos theta c. The value of cos theta c we can calculate from here as the value of theta c, we know it is sine inverse of mu of air by mu of water, that is 1 by mu. So in this situation the value of cos theta c we can write the root of 1 minus sine square theta c is 1 by mu square. So if we substitute the power which is escaping from the water to air is P by 2 1 minus root of 1 minus 1 by mu square. So this is the amount of light energy which escapes from the water to outside region if a point source of power P watt is placed at a depth h below the interface. And here you can see the power which is escaping is independent of h. It only depends on the refractive index of water or the medium in which the source is placed.